Good day, everyone, and welcome to the DOE Fuel Cell Technologies Office monthly webinar series. Today's installment is titled the FCTO Lab Consortia Overview, covering ElectroCat and HyMARC. My name is Chris Worth, and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to the EERE website in about 10 days. We will send out an email to attendees once those are posted to the site. All attendees will be on mute throughout the webinar, so please submit your questions via the question box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. Today we'll be discussing two of our FCTO lab consortia associated with the Energy Materials Network. First, we'll cover the Electrocatalysis Consortium, or ElectroCat, followed by the Hydrogen Materials Advanced Research Consortium, or HyMARC. We'll get a snapshot of both consortia's current and upcoming activities and capabilities. We'll see the role of individual projects that are selected to work alongside these consortia, and how they may utilize existing consortia capabilities. Finally, the FCTO will provide some information on our upcoming funding opportunity announcement. I'm joined today by our DOE host, Dimitrios Papageorgopoulos, Fuel Cells Program Manager, and Ned Stetson, the Hydrogen Storage Program Manager within the Fuel Cell Technologies Office. Let's first go to Dimitrios to introduce the ElectroCat Consortia and their presentation. Good afternoon, Dimitrios.
Thank you, Chris. So the Fuel Cell Technologies Office has established 3 collaborative research consortia as part of DOE's Energy Materials Network as an extension of the President's Materials Genome Initiative to foster innovation and accelerate the materials to market process by a factor of 2. So I'm going to highlight today one of these, ElectroCat, which is focused on the development of PGM-free catalysts and electrodes. Next slide, please. So ElectroCat leverages the world-class research facilities and expertise at the participating national labs and addresses challenges in materials theory, computation, synthesis, and characterization. The co-leads of the consortium are Dr. Piotr Zelenai from Los Alamos National Laboratory and Dr. Debbie Myers from Argonne National Laboratory, and partner laboratories include Oak Ridge and NREL, with Karen Moore and Hugh and Din being the representatives of those labs and actively involved in the consortium. From our end, from the DO end, that is, we have myself and Dr. Adria Wilson, who manage the consortium activities. Next slide, please. ElectroCat is concerned with the development of electrocatalysts for fuel cell applications. The primary focus is on automotive, but there are other applications, not only fuel cell ones, that could benefit from the activities of the consortium. So I have a couple of examples, a few examples actually on the slide concerning the use and application of electrocatalysts in, for instance, petroleum refining, production of chemicals such as nitric acid, vehicle pollution control, electronics sector, as well as not only for energy conversion with fuel cells, but the generation of fuel such as hydrogen through electrolysis. Next slide, please. So why are we doing this? Fuel cells need to address 2 major challenges, namely durability and cost. So for being able to get fuel cells to be competitive with incumbent technologies in terms of cost and durability, we need to address various material components such as catalysts. And actually, catalysts are approximately, or close to at least, half of the cost of the stack. So in order to be able to meet our targets cost-wise, not only in the near term, that is the 2020 timeframe, but beyond 2020, and we have an ultimate cost target of $30 per kilowatt, we need to be able to advance the field of catalysis and not only improve performance, but be able to reduce or significantly reduce and eventually eliminate the use of platinum group metal catalysts So PGM-free catalysts lag behind platinum currently in terms of durability, efficiency, performance, and ease of integration into MEAs. So ElectroCat is focused on addressing not only the development of materials that have the activity durability to be able to compete directly with platinum, but also have these to be integrated in actual devices, namely the membrane electrode assemblies. Next slide, please. So we have, as you all know, detailed targets that are outlined in our multi-year research development and demonstration plan. And we have a table that focuses on targets for electrocatalysts for transportation applications. The majority of these are focused on the 2020 timeframe and the use of catalysts that incorporate platinum and other PGMs. But we also have a PGM-free catalyst activity, and that is highlighted in the table shown on the slide, where we want to meet by 2020 44 milliamps per square centimeter at 0.9 volts IR-free, and the activity is measured hydrogen and oxygen. So the reason this target exists is because it would allow PGMs to be able to compete directly with platinum and with other PGM-free catalysts. So the target actually tells us that it's equivalent to PGM catalyst mass activity of 0.44 amps per milligram of PGM at a loading of 0.1 milligrams per square centimeter. Next slide, please. So taking a step back and looking at the strategy for ElectroCat, there's two major components here. One is concerned with materials discovery and development, and the other one with tool development. So one of the objectives of the EMN Consortia is to be able to streamline tools and capabilities that are abundant in our national lab network and to be able to make those available to stakeholders in the research community. So on the materials discovery and development side, we're looking at the development of catalysts for oxygen, deoxygen reduction reaction in low temperature and high temperature PEMs, as well as in phosphate fuel cells, as well as catalysts for both the oxygen reduction and the hydrogen oxidation in alkaline membrane fuel cells. And as I mentioned earlier, one of our goals is to be able to integrate these into electrodes and MEAs that are compatible with PGM-free catalysts. On the tool development side, we're looking at both high-throughput experimental as well as computational capabilities, optimization of atomic scale and mesoscale models of catalyst activity to predict macroscale behavior, high-throughput techniques for catalyst synthesis, as well as high-throughput techniques for characterization, catalyst electrodes and MEAs. And finally, what we want to do is be able to aggregate that data in an easily searchable public database. Next slide, please. So there's been a notice of intent released last month, and it kind of outlines the topic for ElectroCat. So what we're looking for is to be able to develop high-performing and durable PGM-free catalysts and electrodes to significantly reduce fuel cell costs, primarily for automotive applications. Since we're targeting automotive applications, low temperature polymer electrolyte membrane fuel cells is our prime objective. So the goal of the topic is to be able to achieve activity of 44 milliamps per square centimeter of 0.9 volts in a polymer electrolyte membrane fuel cell MEA by 2020. Again, as I mentioned, we're expecting projects to leverage specified collaboration with one or more of the national labs that are involved in ElectroCat, including both the experimental and the computational side of it. These projects are expected to be up to 3 years with interim go, no-go decision points. And I think, last but not least, interested applicants are encouraged to interface with the ElectroCat steering committee to determine potential for collaboration. And this, and I stress this, needs to be done before the funding opportunity announcement is released. Next slide. So with that, I'll hand it over to Dr. Debbie Myers and Dr. Piotr Zelenay, who who will highlight and outline the capabilities that currently exist in the consortium.
Okay, thank you, Dimitrios. So I would like to give a brief introduction to the ElectroCat website and the organization of the capabilities, and then Piotr will go over in detail the various categories and how those capabilities can be used. So back in February of this year, we established a website for ElectroCat with the address of www.electrocat.org. And within that website, there's a page that describes the capabilities. We have approximately 40 capabilities at the 4 different national laboratories, and those are organized into 3 categories, being synthesis, processing, and manufacturing, characterization and testing, computation, modeling, and data management. Within each one of those larger categories, there's subcategories dealing with high surface area catalyst, model systems, and implementation of those materials in membrane electrode assemblies and characterization of those materials. The last category, computation, modeling, and data management, involves density functional theory, calculation of active sites and stability of materials, for example, and also methods and models to characterize behavior in membrane electrode assemblies. And finally, systems for handling and correlating that data that's coming from the national laboratories and also from FOA respondents. So in the upper left corner, I show a screenshot of the capabilities page, and that's organized in 3 columns which correspond to the 3 different categories for the capabilities. Next slide, please.
Right, can you hear me?
Yes.
Okay. All right. So I will take it from here. This is Piotr, and I'm speaking from Los Alamos National Laboratory. I will just, however briefly, and we apologize that due to interest of time, we need to be so brief when introducing those capabilities. But I would like to address in some greater detail the subcategories that Debbie mentioned just a minute ago. So the individual capabilities by different national laboratories have been broadly formulated, and you will notice that some capabilities cut across different subcategories as shown in the next 3 slides. So the first group or first category is synthesis, processing, and manufacturing capabilities, starting with high surface area catalysts. These are the materials that have been dominating the field of PGM-free electrocatalysis to date. The capabilities exist in this field in all 4 national laboratories making up ElectroCat, starting with PGM-free catalyst synthesis, analytical characterization, and electrochemical and fuel cell testing, which is one of the main capabilities at the Los Alamos National Lab. We also have spotted deposition of thin films, by which method we can also create high surface area catalysts. That capability exists at Oak Ridge. And we also have a powder spotter and implant system at NREL, which can be used to synthesize catalysts as well as modified existing materials by, for example, ion implantation. Then the lead capability at Argonne National Lab is high throughput synthesis of PGM-free catalysts and electrodes, which has already been demonstrated for PGM-free systems. Then we've been working on model systems synthesis already for some time. At Los Alamos, we've been looking at controlled functionalization of model catalysts. Then we have spotted the position of thin films and high surface area catalysts at Oak Ridge. This is one of those cross-cutting capabilities I mentioned earlier. And another one is high throughput thin film fabrication and characterization at NREL. Now, if in the fuel cell fabrication subcategory, we are looking predominantly at membrane electrode assembly fabrication. That capability has existed at Los Alamos for many years. Relevant to this subcategory is high-throughput synthesis of PGM-free catalyst at argon, as well as high-throughput approaches to scaling PGM-free electrodes as required in the future. Now, the last but not least, there is a manufacturing of porous electrodes existing at Oak Ridge. Now, next slide, please. In the next slide, we are talking about characterization and testing capabilities. These are long lists in 3 different subcategories. Starting with, again, PGM-free catalyst synthesis analytical characterization, as well as electrochemical and fuel cell testing at Los Alamos. We also have significant X-ray characterization capabilities, such as RDXRF at Los Alamos and very relevant X-ray photoelectron spectroscopy at Oak Ridge. Then the microscopy-related capabilities at Oak Ridge, or electron tomography, analytical electron microscopy, and in situ electron microscopy. And then we have a slate of capabilities at argon, having to do with structure, composition, function relationship, and the active site determination, several in-operand methods for determining atomic, nano, and microstructure characterization, combinatorial hydrodynamic screening, which has been established recently at argon, and then high-throughput characterization of PGM-free catalysts and electrodes. Electrode and cell characterization include operando differential cell measurements of electrochemical kinetics and transport at NREL. Relevant here is the already mentioned capability at Los Alamos, having to do with PGM-free catalyst synthesis characterization and testing. And then we are looking at electrode microstructure characterization and simulation with argon. And 2 capabilities at Oak Ridge National Lab, electron tomography, analytical electron microscopy. And then we are going back to argon's in situ operando atomic nano and microstructure characterization, which can be applied to electrode and cell studies. Then segmented cell capabilities exist at both NREL and Los Alamos, and has been those capabilities have been demonstrated for low PGM systems, and they are about to be demonstrated for PGM-free ones. Then at Los Alamos, there is in situ fluoride and carbon dioxide emission measurements capability, which is relevant to degradation of the carbon and ionomer-based electrodes. And then as well, also segmented cell and neutron imaging. And finally, the high throughput characterization is at argon is very relevant to electrodes and cells. Now, model systems characterization include controlled functionalization of model catalyst, that is by the method, so-called enable method. Then X-ray photoelectron spectroscopy at Oak Ridge, and high throughput thin film fabrication and characterization and NREL, which is in gas phase in a high vacuum. Now, next slide, please. We are moving on to the last busy capability slide. On computation modeling and data management. Starting with catalyst modeling, that one based predominantly on first principles has been established and demonstrated for PGM-free system at Los Alamos. Then electrode and fuel cell focused modeling efforts are led by Argonne National Lab for ElectroCat. And then finally, both NREL and Argonne are responsible for data management part of the consortium, which will become very important once the amount of data produced is gonna go up. So with that, next slide, please. I'm giving it back to Debbie for capability navigation.
Thank you, Piotr. So I'd just like to briefly describe how to navigate the website and learn more about these capabilities. And I took a snapshot of just the materials characterization page. And one of the capabilities that I decided to highlight in this was the analytical electron microscopy at Oak Ridge. So if you click on a particular title for a capability, this will take you to a page that describes the laboratory responsible for that capability, the capability expert, and then details about each one of those capabilities, how it's been used in the past for PGM-free catalyst characterization or electrode characterization. if there's any limitations to that capability, what the availability of the capability is for the consortium work, and then also some literature references where this capability has been applied to catalyst systems, and then finally some graphics describing the capability. So if you have specific questions about a capability, I encourage you to either go through the steering committee or to contact the person directly listed as the capability expert on each one of these pages. Next slide, please.
So thank you, Debbie and Piotr. I have one last slide on ElectroCat, just to conclude, and I'm going to hand it over to HyMARC. So in principle, questions about capabilities, as Debbie mentioned, please contact the steering committee members. For the FOA, there is a site on there that can guide you through that process. And any interaction, as I mentioned earlier, with the steering committee members on the capabilities should be done prior to the full-out release. Also, as a note, if you intend to interact with ElectroCat through a full awarded project, please do not contact either steering committee members or capability experts after the full has been released. So that's basically me repeating my previous statement. And with that, I would like to thank both Piotr and Debbie again, and I will hand it over to Chris for HyMARC.
Thank you, Dimitrios. And I will in turn go back over to Ned Stenson. Ned's the program manager of the hydrogen storage program at the Fuel Cell Technologies office. I believe he's going to start out with a little introduction for the HyMARC as it relates to the upcoming FOA, and then we'll get more into the HyMARC capabilities. Ned, are you there?
Yes, thank you, Chris. Good afternoon, everyone, or good morning as appropriate. And as Chris mentioned, I'm here to just give you a quick introduction to the HyMARC FOA topic. So we established HyMARC about a year ago, a little over a year ago, and this is the second consecutive year that we've run a topic to select seedling projects to join the HyMARC team. HyMARC was established to try to accelerate the development of viable hydrogen storage materials for automotive applications. And we have a lot of similarity with ElectroCat and the other EMN consortia, but at the same time, HyMARC does have a few subtle differences. So we are looking for high-risk, high-reward seedling projects. So by seedling projects, we mean that we're looking for projects that we will come in and commit to a first phase of funding. We expect the projects to work very closely with the HyMARC team to accelerate the progress and development of the material concept that they propose. And in the first phase, to demonstrate the feasibility of the concept. Once the demonstration of the feasibility has been met, then we will commit to fund the additional phases for the full project. So we are expecting projects proposed as up to 3 years in total length, with DOE funding up to about $1 million in total. However, the first phase is limited to maximum of 12 to 18 months and $250K of funding. And as I said, we are looking for high-risk, high-reward projects that have potential to meet the onboard storage goals. So with that, I'm actually going to turn over to Dr. Mark Allendorf of Sandia National Laboratories. Mark is the director of the HyMARC Lab Core team. So Mark, it's all yours.
Thanks, Ned. Hello, everybody. I'm here to give you a little overview of HyMARC and its research activities and the capabilities that we're developing. HyMARC is a consortium of 3 national laboratories, Sandia National Laboratories in Livermore, California, where I'm located, Lawrence Berkeley National Laboratory, and Lawrence Livermore National Laboratory. Next slide. So in case you're not aware, there's been a huge amount of research that's been devoted to developing solid-state hydrogen storage materials for vehicular applications, and over the years a great many materials were studied and synthesized and characterized, with the unfortunate result that there still are none that fully meet all of the DOE targets, as are shown here in this plot. So at a meeting about a year and a half ago of people actively involved in storage research, there was a convocation to answer the question, why is it that we have been unable to come up with materials that can meet these targets. What is standing in the way of doing this? So next slide. So the answer basically is that there's a large number of physical and chemical phenomena that are not understood sufficiently well that effective materials discovery can be done. So the goal of HyMARC, in fact, is to address these. We're essentially taking a step back from materials discovery and looking at more what we call foundational scientific issues that are blocking effective materials development. So for example, in this cartoon here, you'll see that there are processes that occur essentially all length and time scales within the uptake and desorption of hydrogen. So for example, surface chemistry, interface reactions, bulk diffusion, nucleation of new phases, all of this occurs, and very little of it, in fact, is really understood with the kind of depth that would allow predictive design of materials. Next slide, please. So HyMARC was initiated with the goal of addressing these foundational issues, and basically we have two main thrusts. One is to work on this scientific side of things to address the known barriers that haven't really been understood well, but in the process of doing that, our second goal is to develop capabilities that can be used by people who would be implementing or testing new ideas for developing hydrogen storage materials. So what you see here in this cartoon on the right is this core laboratory team. We have about 30 people involved here, research staff and postdocs primarily, who are working on specific scientific questions, and then also developing as a consequence these new capabilities that will be made available to the projects that are funded out of the FOAs, such as the one that Ned has just referred to. So basically our community tools and capabilities that we're developing right now consist of theory simulation and data mining tools, controlled synthetic techniques, and then new in situ characterization tools. Many of these are available now to be used to help new projects. Some are still under development. And at the end of the presentation, I'll give you a website. HyMARC has its own website which lists the capabilities. You can take a look at that and see what the status is of these various items. I should just mention that the capabilities that we show on the website right now are the ones that we essentially consider to be unique to HyMARC and very specific to storage materials. We have a large suite of diagnostic tools, for example, the routine spectroscopies and microscopies that virtually all national labs have. So if you don't see them there, it's not that they're not available to be used. They almost certainly are. And if you have a specific question about that, you can direct that through a portal on the website. Next slide, please. So one thing that I want to emphasize here is that in the past, the storage synthetic development has really focused on the thermodynamic aspects of storage materials, either the heat of adsorption for adsorbent or the heat of desorption and then reabsorption by a metal hydride. But we've come to recognize that we have to consider kinetic issues as well. So in a kind of conceptual framework, we're thinking about the effective thermal energy for hydrogen release from these materials, which basically breaks down the research activities in HyMARC into two pieces. One is the thermodynamics of uptake and release, and the other is the kinetics of uptake and release. So there are tasks that are targeted to each of those, focusing on mainly on adsorbents and metal hydrides, but we do see relevance of what we're doing to also liquid phase storage materials. So if that's of interest to you, don't give up hope. We're working in that area as well. On the kinetic side, surface reactions, mass transport, solid-solid interfaces, and what used to be called catalysts, but what now we're recognizing more broadly are as additives that affect the kinetics and thermodynamics of these storage materials. So they're broken down along these different tasks. Next slide. What you see here is the organizational structure where we have a lab staff member who is the lead person for each of these tasks. The tasks are very horizontally integrated, however, so the teams that are working on them include individuals from all three laboratories. Two important things that I want to point out here are that we have user agreements with two basic energy sciences facilities. One is the Molecular Foundry, where we have access to a number of synthetic and characterization tools. And the other is the Advanced Light Source at Berkeley, Lawrence Berkeley, where we are developing and using soft X-ray tools to probe various storage materials. For the Advanced Light Source in particular, we now have what's known as a approved program, which gives Sandia and the other two consortium members a block of time on a couple of end stations over a period of 3 years. Now, these tools are very specialized, and it is still a user facility, so we will not be making this particular suite of tools broadly available. However, for projects that are supported under the FOAs, we're collaborating very closely with the research teams, and when it becomes clear that an important question can be answered only by the use of one of these specialized tools at the ALS, we will make time available for that. Next slide, please. So what we've recognized is that storage materials, in particular solid state ones, are affected by a broad range of time and length scales, and as a result we are developing experimentally validated computational models that are intended to span this entire range of length scales and time scales. So on the smallest length scale, we're doing quantum Monte Carlo techniques, I'll talk about in a second, and then that goes all the way up through conventional DFT into kinetic Monte Carlo, and finally phase field modeling, where we're actually looking at reactions that lead to the formation or disappearance of multiple solid state phases. Supercomputing facilities at all three institutions are being used, and again, the modeling teams here are working very closely across all three laboratories to develop these. Next slide. So very quickly, I'm going to go through just a couple of the capabilities in modeling and then go on to synthesis and characterization. For those interested in sorbents, the key issue with sorbents is trying to achieve a strong enough binding of hydrogen at room temperature to have a sufficient volumetric capacity. One of the big issues is that the conventional techniques, even density functional theory, do not do a wonderful job of predicting the stronger interactions with absorbent that go beyond physisorption. So what we're doing is actually collaborating with another team called HyScore within the Fuel Cell Technology Office. They're developing computational tools for predicting, for example, the interaction of hydrogen with an open metal site on a metal organic framework, and we're validating that using a tool, quantum Monte Carlo, which can in principle solve the Schrodinger equation exactly. So by doing this, we can validate these other computational tools. And next slide. This is intended to lead to validated force field models that can be used to predict the uptake and desorption of hydrogen. So what you can see here, for example, is that conventional force fields like the UFF do not do a particularly good job of predicting the uptake of hydrogen with open metal sites on a MOF such as HKIST-1. This is a goal that we're working on now, is to get these improved force fields. Once those are in place, they will be available to use high throughput screening tools like the ZEO++ code, which allow you to input a set of design characteristics and then screen through a large number of structures and databases to select out those that appear to have the best likelihood of meeting those criteria. Next slide. So we are also looking at solid-state thermodynamics, and in particular, we're trying to implement codes that will allow us to model the thermodynamics of nanoscale materials. And so, for example, here we show lithium amide, where it's known that when you react it with hydrogen, you eventually cause a kind of core shell geometry to form, where you have little isolated islands of intermediates, and the model and subsequent characterization have shown that as you shrink down the size of these hydride particles, you can eventually get to the point where an intermediate, this Li2NH, no longer forms. So this is the kind of information that we're trying to develop so that for new materials we can predict the effect of nanoscaling on the thermodynamics and kinetics of the material. Next slide. Eventually, this kind of information leads to the ability to predict kinetic aspects such as the diffusion of hydrogen within a material, or the mobility of dopants such as a nickel catalyst, deflect formation and migration barriers. These are goals, I should say right now. We are beginning, we're only in about the beginning of the second year of HyMARC, and so we have our initial pilot models that we're working on here and are now developing the experimental data to test them. So a number of these things are, as I say, in early stages, but if they are of interest and you think that they might be important if you choose to submit a proposal to the FOA, then before doing that you might want to contact us to get some more information on the status of their development. Next slide. We're also looking at interfaces. Interfaces are particularly important in solid-state materials like metal hydrides, where you can have phase separation. But we are also looking at gas-solid interfaces, where you have, let's say, molecular hydrogen adsorbing onto the surface of a sorbent and then moving around until it actually encounters a high-energy binding site. Next slide. So this is just a brief summary of various modeling capabilities that we have. I just put this up here for your further reference later. Some of these are also listed on the website, as I said. So take a look at this, and if you have further questions, get in touch. Next slide. So synthetic capabilities are extensive within HyMARC, ranging all the way from relatively conventional tools such as controlled atmosphere ball mills to some very specialized nanoscale platforms that we're developing to study the interaction of additives with hydrogen and the effect of nanoscaling. Again, the intention here is to try to cover the relevant length and time scales and to be able to produce reproducible materials with standard procedures so that others can make the materials and achieve the same results. Next slide. For our scientific program, we're proceeding from what we call model systems, which are very simple and generally pretty well understood materials like magnesium hydride, but we're using these as platforms to develop our capabilities. And then we're gradually increasing the complexity from there to things like sodium alanate, which is a so-called simple complex hydride, or simple bulk to nano transitions, and then ultimately moving to the materials that are really of greatest interest for hydrogen storage, but are much more complex to study, such as magnesium borohydride, where you not only have multiple solid phases, but you also have sort of pseudo-molecular species that are appearing. So again, this is broken down along the lines of the different tasks with sorbents and metal hydrides. Sorbents primarily, the concern is thermodynamics, metal hydrides, both thermodynamics and kinetics. Next slide, please. As I mentioned, we do have extensive capabilities at Sandia, and particularly for doing ball milling of materials of various amounts and under controlled conditions. This material or this equipment is available for use in collaboration with HyMARC, and has allowed us, for example, to look at the effects of dopants like titanium on metal hydrides and their thermodynamics. Next slide. A particularly unique capability that we have that we've just brought online is a high pressure station. This is a reactor that can go up to 1,000 bar of hydrogen and can be heated up to 400 C. It will accommodate up to 4 samples right now, and what we can do here is input, let's say, material like magnesium diboride, heat it to high temperature under high pressure of hydrogen, and then look at the uptake of hydrogen and offline analyze the material to see what the effect of those reaction conditions are. This is online now and is available to be used in collaboration with HyMARC investigators, and it's discussed with a little bit more detail than in the schematic on the website. Next slide. Finally, we are developing some new nanoscale platforms using graphene nanobelts and graphene oxide sheets. Here the idea is to be able to make controlled size, controlled composition metal hydrides. What this slide shows is our first work on this, where Jeff Urban's group at Lawrence Berkeley developed these composites of magnesium nanocrystals. These are encapsulated in reduced graphene oxide, and these materials are impermeable to all gases except hydrogen, and the size can be controlled. So this provides a very nice platform for studying nanoscale effects in metal hydrides. Next slide. In addition, however, Jeff is working with Felix Fischer at UC Berkeley, where they're looking now at these graphene nanobelts. And here the idea is to functionalize the edges with transition metals that can serve as catalysts for hydrogen uptake. And here you have a very uniform, flat, graphene-like surface with the metal catalyst in a known location and known chemical environment. So we are developing these as a way of studying and probing additive and catalyst effects and their relationship to metal hydrides that would be formed on the surface of these graphene layers. Next slide. Okay, last but not least, characterization tools. Again, with the models spanning all the way from literally the angstrom level all the way up to micron or even above, we have to have characterization tools that can probe all of these levels. So very briefly, I'll tell you about a couple of these. Next slide. They basically fall into two categories: surface tools and the X-ray, soft X-ray tools, where we're trying to look at interactions of hydrogen on the surface and then and also on the below the surface and at interfaces. Next slide. If you're not familiar, it's important to know that very few techniques can actually look at hydrogen directly. It's possible to see hydrogen as it's desorbed, like using temperature programmed desorption, but to actually probe it on the surface in the initial atomic layer is essentially impossible with almost all techniques. However, if you go to the next slide, we are developing tools and have them online already that can do this. And in particular, one of them is low energy ion scattering, which you see up here in this chart at the upper left. This scatters ions off of a surface. It's basically like billiard balls, knocks hydrogen off the surface, and we can use that to either determine whether hydrogen was bound, but we can also use it to probe diffusion of hydrogen back into the space where the hydrogen had been desorbed. Other tools like X-ray photoelectron spectroscopy, OJ, we have these available, and they can probe with different kinds of particles the energy and absorption at different levels within a material. Next slide. Yeah, this is just on the low energy ion scattering. This is a unique tool. We have it at Sandia and would be available. It's online now. Next slide. X-ray photoelectron spectroscopy is extremely useful, particularly for metal hydrides, but also for looking at additives and catalysts on surfaces. We have this available at Sandia. It's a standard XPS instrument, so that means it's UHV. However, we're in the process of developing a near ambient pressure XPS that will allow us to get up to something like realistic pressures. We think up to possibly 10 torr in situ. In a later slide, I'll also tell you that the Advanced Light Source has this tool as well, and we do have access to it. Next slide. So just again, a quick summary of the surface capabilities that HyMARC has. Next slide. The advanced light source, we have time on 2 different beam lines. One of them gives us access to X-ray emission and absorption spectroscopy. If you could click twice. Thank you. So this is a tool that allows you to either look at the bulk material, which if you look at essentially X-ray fluorescence, you integrate the fluorescence, that probes down into the bulk. Alternatively, if you collect total current as a result of being exposed to the soft X-rays, you actually probe the near surface region, like within the first nanometer or 2. So we have access to this. Next slide. Going along with this, we have computational tools, which are very important for interpreting these data. I'm a chemist, and I have to say I cannot look at an X-ray absorption or emission spectrum and immediately tell you what I'm looking at. And sometimes it isn't even all that evident to people who are the experts. So as a result, we are collaborating, have on our team a theorist at the Molecular Foundry, David Prendergast, who's an expert on this, and he's developing the codes that will predict the spectral signatures of things like magnesium diboride so that we can look at newly synthesized materials and tell you what's there. Next slide. Let's see, finally, X-ray spectrum microscopy. So this is a tool that has never been applied to hydrogen storage materials before, but we are very optimistic this is going to be very revealing when it comes to looking at chemistry at interfaces between solids. So this would be for materials where you have a phase transition. So for example, if you take sodium alunate and decompose it, you get sodium hydride and aluminum metal. So we're developing the sample handling techniques for being able to do this. Because hydrides are air sensitive, this is requiring quite a bit of effort on our part to figure out just how to do this, but we've had some encouraging preliminary results. The really interesting part of this is that with the current instrument that we have access to, we can get around 25 nanometer resolution, so we can actually scan across phase boundaries. But our target is eventually to develop the technique so that we can extend this to an even higher resolution tool called tychography. And tychography, in principle, can give you resolution down to just a handful of nanometers, 3 to 5 nanometers. So it should be possible to actually eventually look at phase nucleation within a hydrogen storage material as you've heated it up and reacted it with hydrogen. Almost done. Next slide. We have developed sample handling capabilities so that you can take a air-sensitive sample and transfer it to either a UHV chamber or to the advanced light source. Next slide. Again, just a summary of X-ray techniques. Next slide. Finally, our ultimate goal is to develop databases that will have thermodynamics, kinetics, and other properties for storage materials that can be used to do data manipulation and large-scale screening and design of materials. So this is our long-term goal. We don't have any on our website about this now, but through the collaboration with the FOA projects and within our team, we'll be developing these databases so they'll be available to the entire community. Next slide. Here's the website, HyMARC.org. We have the capabilities, contact information, and recent news. Please take a look at it. If there's something that isn't there that you need information on, please let us know, or if you have any questions. Final slide. Thanks very much to the Fuel Cell Technologies Office for their support of this work, and they'll be happy to answer questions. Turning it over to Chris now. Thank you.
Thank you very much, Mark. Very good presentation. We're going to go back to Dimitrios and Ned now, and we're going to field some questions and answers, questions that were submitted throughout the webinar here. If you're still interested, the question line is still open, so head there and type in any questions that you may be thinking of. Ned and Dimitrios.
Thank you, Chris. This is Ned. We do have a number of questions which have been submitted, so as Chris mentioned, if you have questions, please submit them, and we have about 10 minutes to respond to them. I will take the first couple, and I'll turn over to Demetrius for a couple. We have several questions regarding the expected release date for the FOA. Unfortunately, we can't actually give you an exact release date. We can tell you they could be at essentially at any point in time, so we do recommend that if you want to interact or have discussions with the FOA team or the lab teams, you do it as soon as possible. We do have another question asking if national laboratories that are not team members in the two consortia, will they be able to be on teams? And the answer is yes. If you're not a member of the consortia, you can be a team member on one of their proposals. So with that, I'll turn over to Demetrius for some ElectroCat questions.
So there are a couple in that seem to be relative to ElectroCat. And the first one, the potential applicant asked whether he or she needs to select a lab or an expert first. And I think the answer to that is that basically what we're looking for is to select capabilities that would actually be a benefit to the application. So not specifically a lab, but a capability which would include an expert. And the second question that I can see has been posted relates to whether ElectroCat applicants need to bring something specific to the table. And with all those capabilities that ElectroCat and, for instance, HyMARC has, whether they, what is it that the applicant brings to the table? And as I outlined in the presentation earlier on, and as is outlined in the notice of intent, what we're looking for is for the submission of novel and innovative concepts that advance the development of platinum group metal-free oxygen reduction catalysts and electrodes for PMFC applications. So what we're looking for is for the applicant to submit a proposal that's innovative, that's novel, and that what we request is for them to utilize the capabilities that exist in the consortium.
All right, so we just got another couple of questions, one relating to HyMARC and asking if there's experimental and computational techniques that could augment HyMARC's existing capabilities, if that was of interest. The HyMARC proposal is specifically for advanced hydrogen storage material concepts. It's not actually looking to augment the HyMARC capabilities. It's actually for development of specific material concepts. So that's what we're looking for in this FOA topic. Okay, another question. Can you provide an example of an early breakthrough from the HyMARC effort? Well, unfortunately, we are just kicking off the HyMARC. It's been going for about a year. The lab's been basically set up the resources and developing the computational tools. We actually just kicked off the new projects that were selected through last year's FOA. So we are actually just really starting the real R&D work in HyMARC. So at this point in time, we cannot give you an example. However, hopefully next year we will have examples for you. So I think that's all the questions we have submitted at the moment. So again, if you have any questions, please try to get them in quickly.
And with that, I think we can hand it over to Chris for some housekeeping, final thoughts and statements.
Great, thank you, Demetrios and Ned. I guess I'll just remind everyone here that the webinar recording and slides will be posted at the EERE website. The slides should be available in a day or two. I will email everyone directions and links to where you can access those slides for download. Again, if you want further information, hydrogenandfuelcells.energy.gov, that website listed there, is a good resource. You can sign up for our newsletter, you can register for more upcoming webinars, etc. So look for an email when this presentation is going to be available online. I'll personally would like to thank Mark, Piotr, Debbie, Ned, Demetrios for presenting today, and looking forward to the next talk. That's it, everyone. Have a great rest of your week and take care. Bye-bye.